In this college algebra lesson, we're going to talk about the rational roots of a polynomial. Rational roots are also called the x-intercepts or the zeros of a polynomial. They all mean the same thing. They all mean the place where the y value is 0. So when we graph our polynomial, the graph is either touching or crossing the x-axis at those places. They're called roots, zeros, or x-intercepts. They all mean the same thing. If our polynomial that we are working with has degree 1 or 2, we can directly find the x-intercepts by solving f at x equals 0. For example, if f at x equals x squared minus 4x minus 1, we can use the quadratic formula to find the x-intercepts. Looking at the graph of our parabola, we see that there are 2 x-intercepts. One of them is negative and one of them is positive, but I don't know exactly where they are at. So let's use the quadratic formula. 0 equals x squared minus 4x minus 1. And the quadratic formula says x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So we end up with 4 plus or minus the square root of 16 plus 4, all divided by 2. And that simplifies to 2 plus the square root of 5, or 2 minus the square root of 5. So there are the 2 x-intercepts, or roots of our polynomial. But what if the polynomial has degree 3 or more? Unfortunately, there isn't a nice algebraic way to find the x-intercepts. The best that we can do is use a graphing calculator to give us decimal approximations. But what if we don't have a graphing calculator? Then we can use something called the rational root theorem to guess reasonable x-intercepts. So rational numbers are numbers that can be written as a fraction of 2 integers. Examples of rational numbers include a half, 5/3, negative 2/7, and even 3 is a rational number because we can write 3 as 3 over 1. You could write it as 6 over 2. Doesn't matter, it's 2 integers in a ratio. That makes it a rational number. So what does the rational root theorem tell us? The rational root theorem is going to help us narrow down the guesses of where a polynomial has x-intercepts. So here I'm writing a generic polynomial. F at x equals a sub n x to the n power plus a sub n minus 1 x to the n minus 1 power plus so on and so forth, dot, 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 plus a sub 1 times x plus a sub 0. If there is a rational root or a rational x-intercept, then it looks like the fraction p over q, where p is a factor of a sub 0, the constant term, and q is a factor of a sub n, my leading coefficient. So this is the constant term of the polynomial, and this one is the leading coefficient. So let's look at, so the reason why we use this theorem is it gives us a list of possible x-intercepts. So for example, if f at x equals 3x squared plus 5x minus 2, the numerator could be all the factors of 2, which is positive 1, negative 1, 2, and negative 2. The denominator could be all the factors of 3, 1, negative 1, 3, or negative 3, which means that all the possible roots, rational roots, are the fractions 1, 2, 1/3, and 2/3, but also negative 1, negative 2, negative 1/3, and negative 2/3. We have 8 possible rational roots. So what are we going to do once we have all these rational roots? Let's put that back on the board. We're going to check the value of our function at each of these possible roots. So I'm going to make a table. Plugging in positive 1, we get 6. So that means that 1 is not a rational root. If I plug in negative 1, I get negative 4. So that one doesn't work. If I plug in 2, I end up with 20. So that one's not a rational root. If we plug in negative 2, we do end up with 0. So that means negative 2 is a x-intercept for our function. Once you find the root, we can do polynomial division to factor the rest of our polynomial. So we are going to divide by x minus whatever the root was, x minus negative 1. So to do polynomial division, inside the division sign, I write 3x squared plus 5x minus 2. And on the outside, I write x plus 2. And to do division, I only have to look at my leading terms. So how many times does x go into 3x squared? It goes in 3x times. And then we take 3x times x, and that gives us 3x squared. And 3x times 2 gives us 6x. We're going to subtract that polynomial, and I end up with negative x minus 2. And again, we only look at our leading terms. What do I need to multiply x by to get negative x? That would be negative 1. Multiplying negative 1 by x, we get negative x. By 2, we get negative 2. Subtracting these two lines, we end up with 0. That's my remainder. So that means that there is no remainder, or a remainder of 0. Therefore, the polynomial 3x squared plus 5x minus 2 factors as x plus 2 times 3x minus 1. And we can look at this point and see that the roots, or the places where the function would be 0, are at x equals negative 2 and x equals positive 1/3. Now, this was a degree 2 polynomial, so we could have just used the quadratic formula to begin with, but I wanted to show how we use the rational root theorem before I do a little bit larger example. Let's find the roots of the function f at x equals 2x cubed minus 9x squared plus 2x plus 1. The rational root theorem says that the numerator could be 1 or -1. It's all the factors of our constant term. And Q could be +1, -1, +2, or -2 because it's all the factors of our leading coefficient. Putting this together in fractions, the possible rational roots are 1, -1, 1/2, and -1/2. We make our table of values again, and all we're doing is evaluating f of x at each of these. We only have 4 numbers to check this time. So when we plug in 1, we end up with -4. So that means that +1 is not a rational root. If I plug in -1, we end up with -12. So that's not a rational root. And if we plug in 1/2, we do end up with 0. So that means x equals 1/2 is a root. Now we're going to divide our function by x minus 1/2. It's x minus whatever the root is. Okay, so all we have to do is look at our leading terms. What do we multiply x by to get 2x cubed? That would be 2x squared. Then we take 2x squared times x minus 1/2. We end up with 2x cubed minus x. Subtracting that line from the line above, we get -8x squared, -8x squared plus 2x plus 1. What do I multiply x by to get -8x squared? It would be -8x. Multiplying x minus 1/2 by -8x, and then we have to subtract that. We end up with -2x plus 1. And again, we just look at our leading terms. What do we need to multiply x by to get -2x? And that would be the -2. And we see that we get a remainder of 0. So that means our polynomial factors as x minus 1/2 times 2x squared minus 8x minus 2. You may notice that the second polynomial has all even numbers in its for its coefficients. So we could go ahead and factor out the 2. So we get 2 times x minus 1/2 times x squared minus 4x minus 1. And now we've gotten to a degree 2 polynomial. We can just use the quadratic formula. This is actually the same quadratic equation that we did at the beginning of class. And so the roots are 2 plus the square root of 5 and 2 minus the square root of 5. Looking at our graph, it's a degree 3 polynomial. It's crossing the x-axis at the 3 points, 2 minus square root of 5, 1/2, and 2 plus the square root of 5. And for the y-intercept, we just let x equal 0. So we had we end up with y equals 1 when x equals 0. So we get the point 0, 1. And here's a sketch of our degree 3 polynomial. So all of this in our textbook is section 5.5, the zeros of a polynomial function. And the main thing that you have to look for is what are the possible rational roots.